Note the de-energized start state of this system ensures that the internal circuitry of timer relay TR1 is powered up. An operator initiates this system by pressing start. This energizes the F contactor coil and energizes the controlling input of timer relay TR1. These associated contacts immediately change states. The F1 contact closes and establishes a holding circuit, which allows an operator to release the start button. The F2 electrical interlock opens, preventing the braking contactor coil from being energized. The F primary contacts close and the motor accelerates in one direction. Additionally, normally open time open contact TR1A closes. Note this contact will remain closed while the motor is running. However, the electrical interlock provided by contact F2 in the activated open state keeps the B contactor coil from energizing. An operator wishing to rapidly stop this motor opens the stop button. This de-energizes the F contactor coil and the controlling input of timer relay TR1. The associated F contacts immediately change states. The F1 contact opens, removing the holding circuit. The F2 electrical interlock closes, and the F primary contacts open, removing three-phase AC from the stator. The normally open time open contact TR1A executing the off delay, however, remains closed for an additional 2-second delay. This energizes the B contactor coil, and its associated contacts immediately change states. The B primary contacts closed, and fixed DC is applied to the motor. The rotor rapidly decelerates. After a 2-second off delay, normally open time open contact TR1A opens and de-energizes the B contactor coil. The B primary contacts open. When the stop button returns to its deactivated closed state, we return to the de-energized start state of the system. Note that the electrical interlock provided by the B2 contact would ensure that an operator could not restart the motor while it was currently undergoing DC injection braking. Only after the B contactor coil is energized and the motor properly decelerated could an operator return it to forward mode. Alternatively, DC injection braking could be made possible by making use of a timer relay executing the negative edge-triggered one-shot function, also set for 2 seconds. The Plugging with Timers lectures, available at the Big Bad Tech channel, examines a similar circuit making use of a negative edge-triggered one-shot. By all means, pause the lecture and see if you can walk yourself through this circuit to ensure it works as advertised. Really, the only difference between this implementation, making use of a negative edge-triggered one-shot, and our previous one, making use of an off-delay timer, is that contact TR1A does not remain closed while the motor is running, but only closes when in the process of deceleration. Regardless of the timer function employed, the electrical interlock provided by contact F2 in the activated open state while in run mode would keep the B contactor coil from energizing. Before we bring this lecture to a close, let's crack open the DC power supply and see how it affects DC injection braking. Without going into unnecessary technical detail, a DC power supply is ordinarily composed of 2, sometimes 3 parts. The first part is a tapped transformer, which ordinarily steps down the line-to-line input AC voltage to another smaller AC value. The next part is a rectifier, ordinarily a full-wave bridge rectifier, a power electronics device that converts AC into time-variant DC. The final, kind of optional part of the DC power supply is any filtration that may be used to reduce any ripple in the DC output. Ordinarily, the transformers inside a DC power supply used for the purposes of DC injection braking are tapped, and that the AC output of the transformer can be varied such that an appropriate DC output is produced to properly brake the motor. As I mentioned previously, B primary contact on the output side of the DC power supply needs to be DC rated since it's making and breaking connection to DC. However, a contactor can also be used on the AC input side of the DC power supply. When the B contactor on the AC input side is open, the DC power supply is not producing DC. When the B contactor on the AC input side is closed, the DC power supply is producing DC. Alternatively, one could use both an AC-rated primary contactor on the input and a DC-rated primary contactor on the output to make doubly sure the connection to DC is broken while the motor is at standstill or while in operation. All right, that is that for DC injection braking. In conclusion, this lecture took a brief look at DC injection braking used to rapidly decelerate a unidirectional motor by removing three-phase AC and briefly applying fixed DC to the motor windings. Again, DC injection braking is for deceleration purposes only and cannot properly lock a rotor in place. We examined several circuits that did exactly that, making use of timer relay functions. Additionally, we cracked open a DC power supply and showed how its contents affect DC injection braking. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.